Welcome to our second lesson in our Introduction to Material Structure course. Today, we'll be focusing on crystalline materials. Specifically, we'll be defining crystalline materials and comparing them to amorphous materials, seeing how they differ based on atomic arrangement, and then we'll be describing what a unit cell is in a crystalline system. Let's start our discussion by comparing two materials together. The first is quartz, a common crystal you may be familiar with. Quartz helps keep time in wristwatches. Quartz is a piezoelectric, meaning if I apply a mechanical load, I get an electrical response. This is what helps keep your watch ticking. The second material is fused silica glass. This glass is extremely resistant to thermal shock at high temperatures, yet it remains transparent, which can be crucial for specific applications. Why am I comparing these two materials together? Well, they both have the same chemical composition, SiO2. Quartz is, as you may have guessed, a crystal. Crystalline materials are defined as solid materials with a long, periodic 3D arrangement of atoms, ions, or molecules. And they are often opaque, just like our quartz. Amorphous materials, on the other hand, lack this long-range periodic order, and they're often transparent. As we've seen from our example, the crystal structure, or a lack thereof, in amorphous materials has a profound impact on a material's properties. Now, there are benefits and deficits to both, just like any other material. But it's crucial to know if you're dealing with a crystalline or amorphous material when you're designing a product. So now that we know what a crystalline material is and how it differs from amorphous materials, let's dive a little bit deeper. We said in our definition that crystalline materials have this long, periodic 3D arrangement of atoms, ions, or molecules. If we have this periodic arrangement, we have a pattern. If we have a pattern, it's made up of some repeating unit. For crystals, we call this a unit cell. This is the smallest repeating unit found in a crystal. Now, there are many different crystal systems. There are 7 common ones discussed, particularly in metals. We will focus on 3 for now. The first is face-centered cubic, or FCC. The second is body-centered cubic, or BCC. And finally, hexagonal close-packed, or HCP. Both FCC and BCC fit into the crystal system cubic, along with diamond cubic, the crystal structure for materials like diamond and germanium. Now, beginning to think about atoms in 3D arrangements can be really difficult to visualize. I know when I started learning this, it took me a really long time to be able to understand everything that was going on. So I'm going to give you as many 3D examples and 2D visualizations as I can. But if you're finding this challenging, please don't get frustrated. This happens to a lot of people. And if you're starting to get it, well done. Let's start with our hexagonal close-packed system. You can see from my model here that the top and the bottom planes are hexagons, here made out of these blue atoms. And within the unit cell, I have a smaller plane of 3 atoms, notated here in yellow. Remember that when we're visualizing this, that if I was actually in a bulk material, these planes would continue extending. So we're just looking at what's confined in our unit cell. The next is FCC, or face-centered cubic. This gets its name because if we're staring at our cube, there are atoms on the faces of the cube. Finally, we have body-centered cubic, again named because of the single atom that's located in the center of the cube. Now, great, I've defined what these different unit cells are. Why do I need to care what crystal system my material is? I already know it's crystalline versus amorphous. There are many reasons that we need to understand this, but I'm just going to highlight 2 of them here: packing fraction and orientation. Let's start with packing fraction. If we go again to our hexagonal close-packed, it's called close-packed for a reason. It's because these atoms are as close as they can be together, arranged within this hexagonal prism. Now, this can be kind of hard to see with this type of model, which is called a ball and stick model. So let's move to what's called a hard sphere model, where we don't highlight the distance between the bonds. Sorry for the height change. We can see here, again, I have my hexagonal plane, my yellow plane of 3 atoms in between, and my blue plane. We know these are close packed because of how these spheres arrange with one another. Think of a box of tennis balls. If I were to shake it and let the tennis balls fall into their most energetically favorable configuration, the balls on the second layer are going to try to fit into the grooves left behind by the tennis balls of the first layer. And that's exactly what we have happening here. We have our bottom layer with all of these little grooves. The yellow atoms fit directly into those grooves, and then the blue atoms stack themselves on top. Now, this is called AB stacking. I have layer A, layer B, layer A, B, and it continues. HCP has an atomic packing fraction of 0.74. That means 74% of my hexagonal prism is filled with atoms. FCC is also considered a close packed system, but it follows an ABC stacking pattern rather than AB, hence why I have 3 colors in my system here. I have this blue triangular plane, a yellow triangular plane, and then my black plane. Again, this can be really hard to visualize with our ball and stick model, so let's go to a hard sphere model. We have our blue triangular plane. We have our yellow plane, again fitting within these grooves, and finally the black plane sitting on top. Again, remember that these extend within the bulk material. And as I said, this is ABC stacking, which once again has a 0.74 atomic packing factor for FCC. Now, BCC is the odd one out here. This does not have close packed stacking based on where the atom is located in the center of the cube. Its atomic packing factor is only 0.68. Well, why do I need to care about my atomic packing factor? Well, let's say I have a really small impurity atom located within my crystal structure. There are more energetically favorable places, right, spaces in between these hard spheres for these impurity atoms to fit. And as we've discussed previously, materials want to exist in a lowest energy state if possible. The second we want to talk about is orientation. I'm going to use FCC again as an example. If I hold my model up like this, it looks one way. If I rotate here, you're seeing a different view. If I rotate again, well, you're seeing another view. Why does that matter? Well, these all represent different orientations of my model. This is highlighting different directions, so from vectors from one atom within my crystal to another, let's say from the black atom here to the black atom up here, or highlighting different planes, like the blue or yellow planes. For cubic systems, we use what's called Miller indices to label these directions and planes, and we use Miller-Bravais indices for hexagonal systems. Due to time constraints, we won't be going over how to identify these and label them, but it's really crucial to understand what orientation may dominate within your material, and that's due to anisotropy. If you saw our Introduction to Material Elasticity course, you were familiar with anisotropy when we talked about it for composites. Well, anisotropy can exist for metals and other materials too. It's when I have a difference in properties depending on orientation. Take, for example, aluminum. Aluminum has a different Young's modulus depending on what orientation I'm looking at. I show a table here with 3 common orientations in metal systems. Now, maybe this doesn't matter. When we're talking about bulk metallic materials, I often have small little crystals called grains that are all joined together to make my bulk material. Maybe the different orientations of my grains all kind of even out, and so my bulk properties are relatively uniform or isotropic. But depending on the processing conditions, they might not be. So if I'm assuming that my property is going to be one thing, but due to an orientation change, the property is really another, well, my material might not behave as I expect in my final product. Now, metals aren't the only crystalline materials. We can look at our table salt example again, sodium chloride. Its crystal structure is here. This is actually 2 interlocking FCC lattices, one for sodium and one for chlorine. So this crystal is made of ionic bonds. Well, what about covalent bonds? These are often found in ceramic materials. Due to the directional nature of our covalent bonds, ceramic structures often look much more complex than our metals, our FCC and HCP, or our ionic table salt. An example of a word-site structure for zinc sulfur is shown here. With these more complex structures, we can be sure that the bond directionality of our atoms is met. This structure also implies a difference in properties compared to some of the others we saw today. And with that, we've come to the end of our discussion about crystalline materials. There is so much more that we could cover on this topic, but if we're laying the fundamentals here, we now know the difference between crystalline and amorphous materials based on their atomic arrangement, and we've investigated different unit cells for materials and understand some of the reasons why we need to understand the unit cells of our crystalline materials. Our next lesson focuses on polymers. Now, polymers have very different structures than the crystalline materials we've seen here, but some polymers are semi-crystalline. Stay tuned to learn more.